Good morning. And on behalf of myself and the organizing committee, we're very happy to see you all here today. And that's not in the colloquial sense, right? I guess we know what we're talking about. We were very concerned about the weather yesterday. We were really we're in the process of setting up. And as we're setting up, the Houston airport's being closed and it's literally raining cats and dogs. So we are truly happy to see you here today. Couple of housekeeping items, right, before we get started. The Wi-Fi password, right, is on the wall there for anybody that needs it. As far as our agenda goes today, we're going to have 4 talks this morning dealing with CT applications. Then we'll break for lunch. What I wanted to say one thing about lunch is you'll see that on the wall here we have these 2 signs, and it has to do with kind of a signature release. The weird thing about life today is that in order for us to send you emails, if you're interested in them, we need to have your written authority to do that with these new laws that are out. And as a business person, it's a bit of a pain, but I'm thinking if it reduces my spam personally by 10%, I would vote for it immediately. So we'll pass out those little cards during lunch, and for whatever reason, if you don't want to receive emails from us, just don't sign it. But if you do, you'll be on a list about future webinars and seminars and all the types of things that we do. Okay, after lunch, Aya is going to start off with the workshop, actually with a fundamental discussion on CT, right? Theoretical basis of how CT does. And then after that, we're going to separate into 2 groups for what I call the hands-on section. Half of it will be in this room working with Mike Marsh on the data processing, and the other half will be in the lab doing somewhat hands-on with the machines, and then we're going to switch. Okay? So that's the schedule for today. One thing to keep in mind is that everyone's got the radiation rings. So these are important to wear when you're in the lab, and most importantly, don't forget to leave them here, right? So that if you forget to leave, well, I guess not many people are flying, but normally when we have people visit, say if you forget to leave them here, chances are you're going to go through the X-ray machine with them on, and we're all going to have a problem. But that won't be the issue today. Okay, so with that said, we're going to welcome our first speaker, Tom Fitzgibbons from Dow. Okay. So our next speaker is Mike Marsh. Mike is with ORS, Object Research Systems. And Mike has worked in imaging and technology solutions with emphasis on 3D visualization and analysis for over 15 years. I can tell you on a side note, he's also personally responsible for helping me to understand CT over the last few years. All right, his academic training was in biological sciences, but he's been tasked to develop other areas of expertise for commercial development, including material sciences and geosciences. This expertise has led to contributed book chapters, review articles, invited talks spanning these multiple disciplines. His scientific imaging and image processing covers X-ray CT, TEM, SEM, SEM-related microanalysis, and for the last 4 years, Mike has worked as the Dragonfly product manager at Object Research Systems. He's going to talk to us today about image analysis in micro CT. Particularly interesting to me, this transformative advances in deep learning.
All right, and about 45 minutes, is that right?
Yeah.
Okay, yeah. Great. Well, thank you to my colleagues here at Rigaku for inviting me. I'm glad to present. This is something I really enjoy talking about, and I hope you guys learn something and it's informative. And we'll also follow it up this afternoon with some hands-on workshop on some of the topics we discuss here today. Show of hands, who's heard of deep learning? You guys don't read the same news sites I do, so less than half of you. How many of you have done deep learning? All right, we got 1 out of 30.
I did not do it in college, unfortunately.
No learning in the classroom either, huh? Well, we will, if the workshop goes as planned, then you'll all be deep learning veterans this afternoon. How many of you have heard of Dragonfly? Okay, some of you. In Tom's talk, we saw a lot of really terrific image analysis and quantitative characterization done by Aviso. So Dragonfly is a competitor of Aviso. It's an alternative. It's just another software package and solution for doing that sort of analysis. So what we'll do today is I'll give you an introduction about who ORS is and what Dragonfly is. Then I'm going to talk about image segmentation very briefly, because that's what I care about with 90% of my enthusiasm is getting image segmentation done right. So I want to convince you why it's important. Then I'll tell you what deep learning is, and we'll do a little bit of the math and theory on that. And then I'll show you some results of how we're using deep learning in Dragonfly for image segmentation, and at the very end, a little bit on non-segmentation. So, ORS is a small company. We're about 17 people now. We're based in Montreal. We've got my coworker Bill in the back row, who's here in the Houston area, and I'm in Denver, and that's the American team. Everyone else is back in Montreal. And we're an image analysis software company, so we're in the business of scientific image interpretation. We have a software package called ORS Visual, which is for the medical market. But since about 2016, we've had a product for research imaging, for microscopy, and not just research, but industry imaging applications as well. And so the scope of the software that we design is for visualization, for making measurements, for most importantly, for quantitative analysis. And so Tom made mention of the fact that 10 to 15 years ago, when Dow looked at adopting scientific imaging in 3D, there was a deficit in how to process the images. Getting high quality images that inform you qualitatively was not going to be sufficient for making design and engineering decisions. Images are still useful, and biologists have looked at images for decades where they say, oh, in these images the mitochondria touches the nucleus, and in these images it doesn't, so there must be something different about the system. So there are ways of getting information, and qualitative images are very valuable, but I think for a lot of the materials applications you really need quantitative images. And so for us it's all about the quantitative analysis, and the linchpin of quantitative analysis is image segmentation, which I'll try and convince you of. So we have a lot of features, and we try and compete in the market, and I can tell you what the software does. I'm happy to talk to you about it. But deep learning is really the differentiator that we have, that we enjoy, that we think creates the most value for our customers, that sets us apart. Now, and today the workshop is all about micro-CT, and we play in micro-CT both laboratory micro-CT, which is what this is all about, but also industrial CT and medical CT and synchrotron CT. And we're in a number of different markets. So today we'll see examples in this talk. So we just saw examples on foams to other soft materials. In this talk, we'll see some examples from material science, another textile. We'll see some life science and some geoscience examples. So, and we've been around with this product for only 5 years. But we have a very good relationship with non-commercial research centers, and so we have licenses in most institutions around the world. These are the most, we have a lot of research university institutions that use our software. So in the last 18 months, these are places where we've fulfilled or renewed Dragonfly licenses. So we're enjoying a lot of adoption in the academic community. Okay, so it's all about image segmentation, or it's almost all about image segmentation. All these software packages, Photoshop included, ImageJ included, would have image processing tools. I can flip my images, I can scale my images, I can transform, I can crop, I can do filters. And so those are geometry transforms, and I can stitch images together. And when it comes to image filters, I can smooth images and I can enhance contrast. So I'm showing this as the non-differentiator. This is the staple of scientific image processing software, having these capabilities. Everyone has this and everyone relies on this, and these tools are not complicated to use. And there are other image analysis and image processing tools. The quantitative analysis, like we saw in the last talk, where I'm looking at a shape distribution or a size distribution, those tools are now routine. However, none of those tools for the analysis can be used until the image has been segmented. Now, let me elaborate on what I mean. If I have an image, images like the one we see here, in this image, this is a micro CT of a ceramic matrix composite. And if I want to know how many fibers are we looking at? So in cross-section, these fibers are little circles. How many fibers am I looking at? Or this blue coating, how thick is it? Or the pores in the matrix, how big are they? What's the pore volume fraction? You cannot answer those questions until you've done the image segmentation. So all of those quantitative analyses are made possible only after the image segmentation has been performed. The image on the right is not micro-CT, it's actually TEM of rat neurons. Drosophila neurons. And if you want to characterize cell size or mitochondria size, you can't answer those questions until you've segmented. Now, let's look a little more closely at the ceramic matrix composite we were looking at just a moment ago. What you see here, let's look at this fiber, for example. This fiber right here, if you can see it, it's made of a silicon carbide, and it has a thin boron coating, and then there's a matrix around it, which is also silicon carbide. And so it has the same texture and the same grayscale intensity in this image. Outside of this matrix is this material, which is called the exterior barrier coating. And in this image, it's what's out here that's not colored. There's some infiltrating in here, but most of it's what's outside of here that's not colored. And so the takeaway here is the exterior barrier coating, the silicon carbide fiber, the silicon carbide matrix, they're all either like 6 or 7 on the periodic table. They're all aluminum or silicon, and so they have almost no intrinsic contrast. There is enough texture contrast for your eyes, and more consequently, your visual cortex, to see the difference in those materials. But trying to find an algorithm that can separate those is demanding and difficult. And people have been looking at these for 10 years, and no one's written an algorithm to do it. But we're going to talk about deep learning, which is not about writing algorithms. It's about mimicking your visual cortex in the software. So in order for us to characterize the fibers or the matrix thickness or the porosity, we have to segment it. And what we're looking at here is an axial section, and what we're looking at here is a longitudinal section of exactly the same material. And so it looks quite different when you look at it on end, but in either case, the segmentation is very challenging. And here we can look at it even further. As you probe the intensity as you move across this sample, the intensity of all of these materials averages between 148 counts and 152 counts. The scale is arbitrary here. But you can see that it's not like one material is high intensity and another material is low intensity. They're all about the same intensity. So segmentation is very demanding. And the area we're looking at right here is just a zoom in of this area right here. Okay, so image segmentation is required for us to be able to do this sort of quantitative analysis. So that's the motivation, and that's going to be true of the foams, of the fibers, of the grains. Image segmentation is critical. All right, moving on to the next topic. Hopefully you're convinced image segmentation is important, and it has been for a long time the bottleneck of doing quantitative analysis. So what is deep learning? So deep learning, you may have heard of in the media. Deep learning is the ability to use something called multi-layer neural networks. It's a mathematical engine to solve different problems. So it's being used in your, if you talk at home when no one else is there to listen, like I do. I'm talking to my Google Assistant. You may be talking to Alexa or Siri or Cortana. The algorithms that power the voice interpretation are powered by deep learning. If you use Google Translate on your phone, that's powered by deep learning. The fact that self-driving cars can read signs and recognize cars and bicycles that look quite different at different angles and different distances, that's powered by deep learning. This is not a video footage of Obama speaking. He's actually saying insulting, vulgar language in this video, but it's not an actual recording. It's all fabricated. It's a deep fake, and it's powered by deep learning techniques. And this was, you can look up this video, but you may not want to play the sound if you've got sensitive ears. You can play this video on YouTube. So it powers deep fakes, and there was a paper in May of this year. So it's used in medical. There was a paper in May of this year of how you can do mammography image processing and achieve better results than the best radiologist in the country for detecting cancers. So deep learning is powering a lot of things. We're going to talk about how it works in a few minutes. Deep learning is often talked about in the same breath as machine learning and I'm going to give you the clarity and precision of the language. So people that are not informed may use machine learning and deep learning interchangeably. People who are informed are very consistent. This is not just my opinion. There's a consensus on what this means. Deep learning is just one type or technique of machine learning. So people sometimes talk about artificial intelligence and data science, and in the scope of this AI research arena, which has been around since the 1950s at least, there are machine learning techniques where machine learning is defined as any algorithm or system whose performance improves with more examples, more data to learn from. So there are many different machine learning techniques, and one of those techniques is artificial neural networks. And when you talk about multi-layer artificial neural networks, you're talking about deep learning. So deep learning is one type of machine learning, which is just part of artificial intelligence. So you'll find this slide reproduced all across the internet. This is the NVIDIA's version of the slide saying deep learning is part of machine learning, which is part of artificial intelligence. So if I write a program to play chess or checkers, and I play against it, it might feel like I'm playing against something intelligent, but that's just a program someone wrote that follows rules. And so we've had artificial intelligence for a long time. Machine learning started becoming popular when we actually had lots of data available to train algorithms, or to train machine learning models, I should say. And I can find one place for lots of examples is I got a lot of spam in the 1990s. And so it's very easy for places like Google to train machine learning models to detect spam. And now you can train deep learning models to look at videos and say, is this a cat or is this a dog? And it can do it with extraordinarily high accuracy. So I shouldn't say too much about this, but of the different mainstream machine learning techniques, a lot of them do very well with a little bit of training data, but they hit some sort of limit and approach some sort of asymptote. And deep learning, particularly deep neural networks, often start out slower, but keep improving as they enjoy more and more training data to benefit from. So, I'm missing a critical slide. Okay, that's okay. The slide I want to show you just shows you this construct right here. This is an artificial neuron. So an artificial neuron has a mathematical function and it has inputs. So in this case, it's a simple function that's going to sum up some values, where the values are the elements of this x vector, x1 through xn. And when it sums them up, it may also apply coefficients of a coefficient vector, w1 through wn. Well, this is a very simple mathematical construct. It's just adding up a bunch of numbers and then passing on that number. And it may have some rules for how it passes on that number, in the same way that a neuron in your head may not always pass on the signal. In your head, neurons have this action potential which either fires or doesn't fire. And some artificial neural networks have a similar activation function. Sometimes it's linear. In fact, innovation the shape of this activation function in about 8 or 9 years ago was in part responsible for why deep learning has taken off. Okay, so you have this mathematical construct called an artificial neuron. Now, how do you map that onto some data science problem? Well, suppose I give you a table of information I measured on a bunch of animals in my neighbor's yard. And I wrote down the height and whether or not they came when I called them and whether or not they slept all day, but I didn't tell you if it was a cat or a dog. Well, that information is pretty easy to tell with reasonably high accuracy from that table. Is it a cat or is it a dog? And this simple linear model of a single neuron has some predictive value of separating this table into what's a cat or what's a dog. And so maybe this is a certain mathematical function and it ends up saying 0 if it's a dog or 1 if it's a cat. So it's for certain easy linearly separable problems, the artificial neuron works well. What if you want to process an image and say, is this a 4 or is this a 9? So how do you map that onto an artificial neuron? Well, there are different ways of mapping on. Here's a simpler example where maybe I have some tables and some beds and some chairs, and I know the width and the height of each one of them. So what I can do is I can actually make 3 neurons, a bed neuron, a table neuron, and a chair neuron, and each neuron can take the height and width elements. And then it can tell me how likely I think it is it a bed? How likely do I think it's a table? And how likely do I think it's a chair? And then maybe I can take whichever one gets the highest vote. So this has some predictive power. But if I try and replicate the same thing with that image and say, is it a 4 or is it a 9? The data here in my table is actually the intensity of the pixel at every spot in the image matrix. And it's a 28 by 28 pixel image, and it's got 784 pixels total. Well, I could just create 10 neurons, a 0 neuron through a 9 neuron, and hook each one up to all 784 inputs. And I would have this simple layer, single layer of 9 neurons. This doesn't work. If you just try and take some linear combination of all of those neurons, it's not going to give you any predictive power. So the single layer fails. However, we introduced the idea of a multi-layer perceptron, sometimes called the feed-forward network, and now called deep learning. So having one or more hidden layers, and that's what we have here, layers in between the output layer and the inputs, having one or more hidden layers is the hallmark of deep learning. So now we revisit this problem of trying to decode this number with 784 input neurons. Now the next 5 or 6 slides are all, these are all images I've stolen from Grant Anderson's video series on YouTube. If you want to learn about deep learning, spend an hour watching these 4 videos on his YouTube channel, 3 Brown, 1 Blue, and you'll know everything I know about deep learning. So they're really terrific videos. So what he does is he takes this number and he designs a very simple neural network. In this case, 10 outputs, neurons 0 through 9, 784 inputs, and 2 layers of hidden layers of neurons. Now, in this case, he doesn't even justify it. He says, I just started with 2 layers of 16 neurons. So this first layer of neurons is fully connected to the 784 inputs. The second layer of 16 neurons is fully connected to this layer, and the final output is fully connected to the second layer. So each one of these neurons in this layer has 784 input coefficients. It also has something called a bias. This has 16 weights. This has 16 weights. If you take all of the unknowns in this system, there are 13,000 unknowns. So if you want to, you can think of this as just some mathematical optimization problem where I have an input and I want to get an output, and I have 13,000 parameters to optimize at the same time. And that's actually what's happening, but it's happening in a clever way. So I want to take inputs like this and get an output vector that says that's a 7. Now, this is an example of a single neuron. It's got all these coefficients, and it's got some activation function, and it's got bias. Now, how does the network optimize and determine those weights? Well, that's the beauty of neural networks, is solving that problem, which didn't exist with the early neural networks in the 80s, but only existed when someone developed it about 10 years ago, the backpropagation method. So I'll explain it to you now. What you do is you start by randomizing all of these coefficients. You just put random numbers in. Now, if I have a network with random numbers and I presented the 784 pixels of this 3, and I push it through the network is going to give me some sort of output. Those random numbers are going to give me something. And maybe in this case it says, oh, it could be a 3, but it's more likely to be an 8. It's definitely not a 2. So it gives me garbage, random garbage, the first time you put data through. So you get this utter trash out the first time. But we can define a cost function. We can say how right or how wrong is it. And we can say we know the answer is supposed to be 3 with 100% and 0% chance of everything else. So we can define how an error function or a cost function, in this case, it's simply the sum of the square differences of all of these elements. So we know how wrong it is. Well, what I can do is I can put a 3 through and I can write down how wrong it was. And then I can put another number through and write down how wrong it is. I can do that 10 times and say, wow, this is really wrong. And now I can do something called backpropagation. I can adjust the weights in the last layer of the network and then use how heavily those are weighted to adjust the weights in the previous layer of the network. And then I can repeat with another batch of 10 numbers. And you know what? It gets it wrong, but not quite as wrong as before. And I can repeat with another batch. And after every time of evaluating the cost function, I adjust the weights in the network. And I use an optimization function and I repeat. And now I have weights in these network, and it turns out to be predictive. Now, if you want to know what's going on, I'm going to save these next 3 slides for the workshop this afternoon of how the neural network succeeds, because I want to get on and talk about some of the success. But this is just going to talk about how the network works and how it encodes. But at the end of the day, you have a network that is predictive. And so this network, the simple 2 hidden layers, is actually 96 to 98% accurate. And if you use something called a convolutional neural network, the accuracy jumps, it incrementally improves up to almost 100%. Okay, in this case, we're mapping a labeling problem of, is this a 3 or is this a 4 or is this a 9? In our case, we're taking a square set of pixels that have grayscale values, and we're returning a square set of pixels that are segmented. This is my silicon carbide fiber. These pixels are my silicon carbide coating. These pixels are my pores. So instead of mapping 784 pixels to one score, I'm mapping 784 pixels to 784 pixels. But basically, the network topology can still be the same. So there are a lot of analogies of artificial neural networks to biological neural networks. So it really is sort of like what's happening in your visual cortex. The first layer of neurons, the first few layers of neurons in your visual cortex, you have line detectors and gradient detectors, and then you go a little bit further into your network and you have feature detectors that can recognize shapes. And you go a little bit further and there's the mythological grandmother neuron. That is that one neuron that lights up whenever you see your grandmother's face because it's fed in by all the other neurons. So much like that network, we have the first few layers of our network just detect edges and contrast and local gradients. And then the deeper neurons aggregate that information in some meaningful way. So there are other similarities and dissimilarities. I want to say one major dissimilarity is the flexibility of the biological neural network is that I can grow new neurons and make new connections. The artificial neural network, at least what most people work with, all we do is adjust the connection weights between the neurons as the network learns. We don't grow new neurons in response to stimulus. That's the biggest difference between artificial neural networks and biological neural networks. So the Dragonfly approach to deep learning image segmentation, we use a software tool called TensorFlow, which is what everyone else uses. It's developed by Google. I don't know what this plot shows, how popular it is and how many people contribute code to it. It's not the best metric of how popular it is, but TensorFlow is up here. Tiano is from University of Montreal. It's pretty much been retired and displaced by TensorFlow. PyTorch is what Facebook uses. It is growing. Keras is just sort of a sub-component of TensorFlow, if you will. And MCTK is another major player from Microsoft. So in our solution, in Dragonfly, we use this tool called Keras, which is an abstraction that you can use with Tiano or MCTK or TensorFlow. However, in our case, we just use TensorFlow. And what we do is we give users the ability to set up a neural network to train it. And then once it's trained, it works just like an image filter. And you can use it to process any images that look just like it. So you can have your segmentation model that segments closed foams and your segmentation model that segments ceramic matrix composites. And you can just put it on the shelf, and then whenever you have more images like that, you can just pull it off the shelf and use it. And you can also share those models. When you apply the model, there are no parameters to tune. So if I use the trained model, or the guy in the cubicle next to me, or the guy on another continent uses the model, they'll get exactly the same results. There's no operator bias, which is quite different from a lot of the image filters that people use. So the workflow here is, and we'll do this afternoon, the user may paint some pixels of silicon carbide fiber and paint some pixels of pore and say, I know that this is pore and I know this is silicon carbide. And then the software takes the examples you made and uses those to train a network. And then the network you can use at any time you want to apply and segment other data. So other people have demonstrated what these different neural network topologies can do. Our challenge was just to make it useful and make it flexible across a number of different imaging domains and a number of different material domains, make it easy, make it robust, and make it very portable because we want people to be able to share it. So that's how we've responded. So we just make it behave like a filter, just like you're using a filter in Photoshop or anything else. Now, let's talk about some results. So this is a denim fiber sample that was imaged on the Nano 3DX, I think here in the building. And there are 2 types of fiber in denim. I don't know anything about denim. I don't know anything more about denim than what I can tell by looking at this image. except I've also seen it in 3D, which I think is important. And what I can tell immediately by looking at this image is I have big fibers bundles and I have small fiber bundles. And in some cross sections, I see the axial fibers and sometimes I see the transverse fibers. But the grayscale of these fibers have, both the large fibers and the small fibers have great overlap. And so it's, I can't just segment them by intensity thresholding. However, I can paint the small fibers orange and the big fibers blue, and you're going to do this afternoon. We can paint 5 slices of data in 5 to 10 minutes. And 5 slices of data with 5 to 10 minutes of human manual interaction is enough training data to train this neural network. And I can train this neural network on a GPU on Amazon Cloud that cost me $1 an hour. I can train it in 12 minutes. You can also train it on your laptop or your desktop. We're just using Amazon Cloud because that way you all don't have to bring capable computers. We can all just log in and do it on Amazon Cloud. So I can do 10 minutes of manual work and I can train for 15 minutes. And the result is I have a model I can apply to the entire data stack or the entire volume. And so we'll get a better picture of this in the next slide, which is a movie, but this is what the data look like before it's segmented. And after you segment the small fibers in orange and the big fibers in blue, and you say hide the blue fibers, now you can actually see what is the shape of the small fibers. If you were to just try and dissect this data and slice it and look at it, it's very, very difficult. I'm not sure I could succeed in looking at this and detecting this knot structure without doing the segmentation and pulling it apart like this. This is the data set rendered in Dragonfly. We've got our next generation rendering engine, which is coming out in the software soon. And so these are made with that. So it's all part of the software. It's not a separate extension or anything. These videos look a little bit better than the slides because they use the next generation rendering. So here we're just looking at these fibers and we're seeing this. The segmentation, the image quality looks comparable to people that are used to visualizing meshes. You can get very good high contrast views of your segmentation without generating a mesh. If you don't know what a mesh is, don't worry about it. But we use this segmentation visualization technique directly on the grayscale data without having to compute a mesh data structure. Okay, so here's another example. This is from Sydney Pasiornik at PUC Rio in Brazil. I don't know why I capitalized Rio. And in this case, we have a data set where there are pores and there are cracks. And if I put this in front of a human being and I said, label a crack, you would do it properly. If I put it in front of a piece of software and I said, label the crack, it says, I don't know what to do. The cracks are exactly the same intensity as the pores. But it's very easy for you to train and paint out some cracks and some slices and train it. And this is the result of the prediction of go find the cracks and label them differently from the pores. The same thing can be done in reservoir and source rocks if you're interested in oil and gas characterization. This is a CT scan of a rock sample that actually it was imaged under reservoir conditions at pressure and temperature, and it had 2 fluids in the space, both oil and brine. And so I think we're showing we were showing the grains in blue, and now we're hiding that. Now we're showing the brine in orange, and then we show the oil in this magenta or purple. So this is a much lower contrast sample, and it's lower contrast because when you try and do X-ray of a X-ray CT of a rock at reservoir conditions, it has to be in a pressure cell, which means you're putting X-rays through a large metal pipe, if you will, and so you're throwing away some of your image quality in order to image under those conditions. So that's a more challenging sample. Don't take any pictures of this slide. This work will be presented next week at AAPS, the Pharmaceutical Scientists meeting in San Antonio. So I only have one slide on this because I don't want to tease too much of what they're doing. But they're doing automatic pill separation. So they'll scan an entire bottle of pills at Merck, and they'll automatically separate all the pills, and then they put it through a deep learning model to see what fraction of the pills have cracks. And if you look at the image intensity of one of these quick scans, you might see in the back of the room, I don't know if you can see it, but there's a crack in this pill. If you use naive segmentation, you get something like this, but the deep learning pulls it out. It looks like this in 2D and this in 3D. So just this is fully automated, and they run multiple batches of pills and then run the deep learning model. Again, no user parameters, so it can run fully automatically as well. Now, The oldest application of micro-CT that I'm aware of is bone. And I think it continues to be a dominant application that people rely on CT for. So in our software, we've got bone analysis. We're just looking at some promotional slides of what you can do with bone analysis when you want to characterize, in this case, it's a large sheep femur. And bone has, you can't tell in these images, you might tell in some future images, that it has the same material on the surface and on the interior, but the structure is quite different. On the surface, it's called cortical bone, and on the interior, it's called trabecular bone. And this is just showing you a separation of that. And the trabecular bone, when it's visualized in 3D, it has this mesh network that people want to characterize that helps them understand the load that the bone can withstand and some of its evolved properties. If you put mice up in space for 15 days and you come back versus their cohorts that were left on the ground, the trabecular structure is measurably different. I'm not going to show you that. But people study bone. And so Daniela Patton is a graduate student in Carl Jepson's lab at University of Michigan, and she wanted a robust image segmentation for bone. And sometimes their bone samples look like this, sometimes they look like this. Now, the point of this slide is to say you may have beam hardening where this side of the bone ends up bright and this side ends up dark, or you may have variations across scans. In this scan, it's much darker overall. However, she took a few, these are human cadaver femurs that she's scanning. So I think she scanned 50 bones and she took 3 slices of maybe 10 bones, maybe 5 bones. I'm not sure exactly how many. She segmented them, and 2 of her colleagues segmented them, and they took the consensus average and said, that's the ground truth. And now let's train a model that will segment bone, and it will make sure and get all of these pixels equally well as all of these pixels. And this case is not as dramatic as this, but the neural network does. It's not a very impressive figure. The neural network does much better success than a traditional algorithmic method. And the paper that she presented all of this work in September at the Bone and Mineral Research Society meeting in Miami. And she's a very good biostatistician, and so it's very rigorous. And you can read her manuscript chapter if you want, where they've done all the analysis, and you can see how consistent the results are and how much better they are than competing methods. This work, so Carl Jepson's group at Michigan also collaborates with Todd Bedbinner's group at University of Colorado Springs, and Emily is a graduate student there. Emily did the same thing in collaboration. They were working on these at the same time. These are, I think, human vertebrae, and the colors don't reproduce very well, but green is prediction and yellow is ground truth. And in this image, this is the result of the neural network, and all the yellow you don't see is all the places it didn't miss. All the blue, I think all the blue you do see is false negative. So the little bits of blue pixels are where it's slightly deviated from the ground truth. So Emily got very good results on her system as well. And then they also, Daniela also trained a network to separate the cortical from the trabecular bone. And so they're working on the femoral head here. And so they're separating the marrow cortical space from the marrow trabecular space from the cortical bone, even though, like I said, the intensity is basically indistinguishable. And I don't know what I want to show here. There are very good metrics for saying how good do the data agree with the ground truth, but I don't have time to get into that. With the ceramic matrix composite, we discussed it a little bit earlier. This is imaged at the synchrotron. So this work is by Ali Badran at the University of Colorado. He's working with Dave Marshall, who's a ceramics guy. And Ali presented this at High Temperature Ceramics in Bordeaux last month, and then again at MS&T in Portland last month. And so this is the data we already showed you. This is what the fully automatic segmentation looks like. And it's interesting because if you look at this fiber here and this fiber here, you can't tell if it's fiber, which is orange, or if it's coating, because they're both silicon carbide. I shouldn't say coating, I should say matrix. You can tell the pores, which are much darker, in green. But if you look at the longitudinal sections, you don't know which of these stripes is supposed to be orange or blue until it's segmented orange or blue by the algorithm. So here you can sort of see that segmentation. I won't go into the details of the network we used, and we can make pretty movies of it. which is all this is. I'll give you 20 seconds of eye candy, and then I'll go to the next slide. So this is just the next generation rendering showing the same thing we looked at before. Let's move on. Now, this is interesting. I suspect maybe no one in the room is close enough to see the breaks, but they actually took the composite inside the micro CT, and it was under a tension cell with acoustics hooked up, ultrasound transducers hooked up, and they pulled on it until they heard cracking, and they knew that the composite was cracking. And there's, I can't even see it. There's a crack here, and there's a crack here, and there's a crack here and here. And so Ali went through about 100 slices and just traced out cracks. This is not long, intensive painting. It's just tracing out a few cracks. So he did it in about an hour, and then trained a network, and then you can run the network, and now you can see what the cracks look like in 3D, so you can characterize the distance between the cracks, the angle the cracks make with the axis of the fiber, bundle, etc. Besides CT, we use the same solution or the same technique in SEM. So in biological samples, everything looks the same. It's either stained or not stained, and stained kind of goes indiscriminately towards membranes. So it's hard for an algorithm to tell you if you're looking at mitochondrial membrane or plasma membrane or nuclear membrane. But a human who's used to looking at plastic embedded SEM images knows what to do. And so here's sort of a closer look at what the result of the prediction looks like. So on the right is automatic segmentation by the model, where it's segmenting the nucleus in yellow, the mitochondria in red, and the rest of the cytosol and the rest of the cytoplasm in blue. And it's only doing it for the cell body. It's not treating all these small dendrites and axons out in the margins. So I told you could do more than just image segmentation. So you can't tell the difference between these two images from where you're sitting, so I'll zoom in. This is a noisy SEM micrograph, and here's the denoised image. So you're accentuating all of the structure in here that is a little bit lost in the noise, and this is trained in a similar way, but it's using deep learning for denoising instead of image segmentation. I'm almost done. I've got a couple more non-segmentation examples. So another denoising example, this is an SEM micrograph of C. elegans, and you can see the result of denoising. We talked about watershed in the last talk for splitting. There was a paper in the literature last December, I want to say, on using a neural network called deep watershed. So whenever we read a paper that's applicable, we re-implement it in the software. And so this is separating out these grains based on a training data set to separate out the grains of different sizes. So if you have some limitations, like where the watershed, where when you end up compressing the Teflon beads and they become harder to separate, this may be a more robust solution than the standard watershed. And I should say, we're not doing anything clever. We're not inventing anything at ORS 90% of the time. We're just doing software engineering. We're taking all the clever stuff that the academics have been writing about, and we're just saying, let's put this in user-friendly software and make it accessible. So we didn't do this. We just read the paper and re-implemented it and make it possible for you to do it as well. So is Aya in the room? Yeah. So I got this slide at 7:30 this morning. So I haven't really looked at it yet, but we're not using deep watershed like we are here, but we're using something called fiber centerline extraction, but we're doing it with deep learning. So these are the big fibers in the denim, but labeled and separated. So I haven't had a chance to see how robust it is yet, but we're committed to making this work, and that'll be sort of the backbone of our fiber analysis package our fiber analysis solution that'll be part of deep learning. So once you do separate the fibers, you can calculate the tortuosity and calculate the fiber length and those sorts of properties. So Ryan Armstrong is I'm going to call him a hydrologist. He trained in civil engineering at Oregon State. Ryan Armstrong is a hydrologist who has a faculty position now at University of New South Wales. And he published this paper in April. We found it in May, and my team was able to re-implement it in 24 hours because the paper is that good, tells exactly the architecture of the network you need to use, and he published all the data he used. It's all in a public repository, so we're able to use exactly the same data. This is my figure, we made it, but it's Ryan's method on Ryan's data. So what Ryan did is he took some high-resolution images of sandstone and carbonate and some low-resolution images, and he trained a neural network to sharpen the low-resolution images into high-resolution images. So what you're looking at is a 20-micron voxel CT of sandstone, and what you see on the right is what happens after you sharpen it to 5 microns. And so if you want to compare, this is what the 20 micron looks like, this is what the ground truth looks like, and this is what the super resolution deep learning filter is able to reconstitute. So it doesn't get full fidelity in here, but what Ryan cares about is characterizing this pore space and knowing its geometry and its total capacity. And if you're trying to compute it from this image, you're not going to get as far as if you compute it from the reconstructed image. So that's super resolution with deep learning. All right, so we love deep learning and we want everyone to use it. And so that's why we put it in the software. So what we looked at today were some materials like textiles and pharmaceutical tablets and the ceramic matrix composite. It's useful in geosciences. We looked at the iron pellet from mining, and it's also used in oil and gas reservoir rocks. Be patient. I'm going to take like 3 minutes just on the acknowledgement slide.
Okay.
Not really. We looked at image segmentation and SEM. We looked at image enhancement for de-resolution, for super resolution. So Ruslana was the person who got started making our deep learning engine. Benjamin has really been carrying it forward for us. Eric Yin, you'll maybe meet at some of our shows. He travels a lot with us, and he's done a lot of the work. And Nicolas Pichet is sort of the architect of Dragonfly and of the deep learning engine. And so I want to thank Ali Badran for the work he's doing on the ceramic matrix composites. And the rat neuron I showed you, I didn't mention, that's from Angel Paredes at the FDA. I thank Dan Skomsky and his intern this summer who did the work on the tablets. I already mentioned Daniela and Emily at Michigan and Colorado Springs. I want to thank Aya and Katsu for the denim data. And then these people don't even know I'm using their data because they've published it in a repository. They're not partners. I just grab the data and do cool stuff with it. That's the multi-fluid reservoir rock from Martin Blunt's group at Imperial College. Ryan Armstrong's work we just talked about. And the denoising on the SEM micrograph was Keena Scott's FibSim stack. It's like 1,500 slices. It's a heroic microscope experiment. All the data is made available online. And I think we have a little time for questions. I'm done.
Yeah, questions? For class first?
Yeah. Okay, Costa?
Fantastic work. So
thanks.
what can you say if you don't have any expert in the room, right? But you are seeing the image and you want to...
We want the image.
No, you want to tell something about that.
I mean, so what I tell people is if you could segment it today based on what your visual cortex interprets, and you could get the same result next week, then we can train a neural network. If you look at it and you say, I think there's a crack here and I think there's a fiber here, and you try it again 2 weeks later and you put them in different places, then the data are just not there in that signal, or not enough that we think we can train a network. So we don't have any experts in the room. We just have a bunch of computer science guys, and we train all these things just by paying them ourselves. So an expert gives us a few examples, and then we say, okay, I see what you mean. And then it's just coloring in a coloring book. And so you color a few examples, and then you train from there. So it doesn't require specific expertise. However, if you have garbage in, you'll get garbage out. So if you color a bunch of mistakes, then the network will learn an imperfect model and make mistakes too. Mm-hmm. Yes.
So the majority of those, look like there were 2 people on average in those projects from the acknowledgements.
Oh, no, I shouldn't say that. So the Merck stuff, there are other people who may have done some of the imaging. The Merck stuff was done 90% by Xiong Yu and then 10% by his supervisor. And the the bone, sort of the same thing, 90% by Daniela. And then actually, she shared a little bit because there were two other people in the lab that spent a day painting to establish the ground truth.
So approximate project time to do those?
Well,
Back of the envelope?
I mean, a couple days for.
In ramp up time?
No. So, I mean, I'm really selling it short if I say a couple days because they have a lot of the people here invested a lot in imaging and they grew a bunch of mice under a bunch of different conditions and then scanned them all. But the image processing time, if you have the expert that can do the painting and segmentation, you spend a couple hours to half a day preparing the ground truth data, and then you train a model overnight. And if you don't like it, you change parameters and train it maybe once more. Yeah, it's not weeks. It's a couple days for the image processing scope of the research. Sorry.
Last question. So everybody likes to tell us how to do our research, like what to use, and so like at the TAC, they've got ComSol and these other
Right, sure.
involved, and so I'm just assuming that you're here because you're there's a good working partnership between Rigaku and your company. And there's some type of optimization, or this is a better product than ComSol or somebody else, all right? So how would we speak to that? Or maybe I talk to you offline.
Yeah, sure. So ComSol does a ton of great stuff that we can't do.
20 miles wide.
Yeah. I mean, ComSol is great for numerical modeling, and we don't do any numerical modeling today, and we're So by the way, Sheng Yu is a student at UT Austin. I didn't mention his attribute. He's listed as Merck because that's where he interned this summer. But Jackson School of Geosciences has a bunch of Dragonfly licenses and some expertise there. You did say TAC. Are you at Austin? Is that what you meant?
Yeah.
Okay. Yeah. Just contact me. If you're doing non-commercial work, your work is not. If you don't show industry collaborators your work before you publish it, if there's no industry beneficiary, then you can use Dragonfly for free. We don't answer all of your phone calls and emails unless you pay for a support plan. But you can get training or get support. So we can talk more offline. And Bill behind you will answer all of your questions.
Okay.
Anything else?
Tom, go.
Yeah, so how you said like 5 or 6 slices to train your data set. Are you painting the entire slice or portions of the slice?
So you have the flexibility. You can paint a mask and say on this slice only interpret this area as the training data. So this was 100 slices of cracks, but they're very cheap to create. This was heroic. This took 15 slices. Which, I mean, he's got 20,000 slices to process. So when I told him he could get 20,000 for the price of 15, he said, sure. So he had to hand paint 15. And these slices took on the order of an hour and a half to 2 hours per slice. You want to get it right sometimes, well, most of the time. And it was demanding. So that took a lot. They have different examples. All the rocks we've done are 2 to 5 slices, sometimes just 2 or 3 slices. So we've got lots of success cases with just a few slices. We are constantly shocked and have no explanation for why you can get by with so little training data.
Okay. Well, once again, Mike. So our next speaker, right, is Aya Takase, and Aya is an application scientist here at Rigaku, who is basically in charge, of our CT group. And her kind of philosophy, right, in doing this is that she greatly believes that X-ray users to develop analysis and testing methods, right, user-friendly is a key for these X-ray tools, right? How can we make them user-friendly? And you'll see some of that when she shows you in the lab, right? She's worked with the Rigaku engineers now to automate some of the CT stuff that we do. And she holds, she's been with the company, she's been in the X-ray business for over 20 years. And I holds an MA in physics from Tokyo University of Science. So Aya is going to talk to us today about high resolution X-ray CT for low Z materials.
Thank you. So when you think about X-ray imaging, it's a technique known as a way you can see through things. You can use X-rays to see your bones in your bodies. You can see the contents of bags or packages, for example. And you can do all those things because X-rays can penetrate through relatively dense and hard materials. But you can use X-rays to see softer, lighter materials, as you saw, some examples from Tom's presentation this morning. So that's what I would like to focus on in this presentation. So it's about a high-resolution X-ray CT for low-Z materials. And when I say low-Z materials, I'm in general referring to low-density or low atomic number materials such as foams, food, drugs, or plants, insects, essentially most of the organic materials. So this Z value, why does it matter? So X-ray CT is X-ray absorption contrast imaging technique. And X-rays are almost exclusively absorbed by electrons. So the number of electrons or Z value in a given volume you have matters a lot. For example, if you were to use medical X-rays, I'll say to look at your hand with a nail going through it, it would look like this, right? The medical X-rays, or more importantly, the energy those machines use, is optimized to see the details in the medium Z range. So in this picture, the nail is a high Z, right? It's got a lot of iron in it. Bones are medium Z range. It's got a lot of calcium in them. And tissues are low Z. And because the X-ray energy is optimized to look at the bones with a medium Z range, it works very well to see fractures and cracks in the bones, but you don't really see much going on in the nail, high Z, or the tissues, low Z, because those are outside of the range this particular range of X-ray energy can see very well. So one of the key things to remember when you image low Z materials is that when your X-ray energy is not optimal, you don't get a lot of good contrast. You have to optimize the X-ray energy to increase the contrast and increase the image quality. Now, in terms of picking the right energy to see whatever sample you're trying to image, the general rule of thumb is that when you have a small and low density sample, you want to use low energy X-rays. And this is to make sure that at least some of the X-rays are absorbed by this not really absorbing sample. And if you have a large and or high density sample, you want to use high energy X-rays because you have to make sure that at least some of it goes through the sample. So that's the rule of thumb. And we're talking about low Z material imaging, so we need to use low energy X-rays. But what determines the X-ray energy? So to understand what determines X-ray energy so that you can control it, let's take a look at how X-rays are generated. So this is a schematic diagram of an X-ray generator. You have a filament, which is the cathode, and you have a target that works as the anode. And you apply high voltage between those two pieces, and you put some current through the filament to generate thermal electrons. And those electrons are attracted to the target because of the high voltage you're applying between the filament and the target. When the electrons hit the target, X-rays are generated. And what we're interested in here is the energy distribution of those X-ray photons. And that energy distribution depends on the target material and the applied voltage. For the target material, you can use different types of materials, usually metals. You need to have something that has a relatively high melting point because the electron beam is going to heat the target quite a bit. And tungsten is probably the most commonly used X-ray target for X-ray imaging. And we use tungsten because its atomic number is 74. It has a lot of electrons and it has high melting point. And those two factors help you to produce a lot of high intensity X-rays. So it's a really good target to use. And when you use a tungsten target, your energy distribution looks like this. So you have energy as your x-axis and you got X-ray intensity as your y-axis. And it's in general kind of broad peak. And that peak position depends on the voltage you're applying between the filament and the target. And the good thing about this tungsten target generator is you can apply very high voltage, 200 or sometimes even 400 kilovolts, to generate really high energy X-rays. You can shift that peak to higher side by increasing the applied voltage. So that is really good if you want to look at heavy or relatively large samples. You can use it to probably medium density, medium sized samples as well. But tungsten is not the best target to use to image low Z materials because you have to lower the applied voltage to shift that peak towards the lower side. And when you lower the applied voltage too much, you lose too much X-ray intensity. So there is a limit of how low you can go with the tungsten target. So this is not an ideal material for X-ray target if you want to image light and small samples. So if tungsten is not the best target, are there any better target materials? And there are a couple of different things you can use. Molybdenum is one of them. If you use molybdenum as your X-ray target, instead of kind of broad spectrum, you can have really sharp peak at 17 keV. And that is called the characteristic radiation because that 17 keV energy is characteristic to the molybdenum material. There is a little bit of broad spectrum at the bottom when you use molybdenum. That's this part. But the main X-ray photons you're getting from molybdenum target is the 17 keV energy. It's really narrow bandwidth and high intensity. So it's a really convenient radiation you can use for low energy imaging. If 17 is not low enough, you can use copper because copper's characteristic radiation is at 8 keV. If you need something even lower than that, then you can use chromium. Chromium would give you 5.4 keV energy radiation. So those are typical 3 different target materials you can use if you need really low energy X-rays, but you don't want to lose a whole lot of X-ray intensity. Now, how much of a difference does it make depending on the energy of X-rays you use in terms of contrast? So let's take a look at some examples. So this is just a 2D projection image collected on styrofoam sample using molybdenum radiation. Styrofoam, as you know, is very, very light. It does not absorb X-rays much. But because 17 keV is relatively low energy, you see a little bit of something in the styrofoam. If you use copper instead, 8 keV, you can increase the contrast a little bit. And if you use chromium, you can see it even better. So this is just one of the examples, but where you see the lower energy helps to increase the contrast when you're trying to look at something really light or small. I want to show you another example of this sample. This one is on organic film, and it is only 80 microns in thickness. And it has 3 micron thick membrane filter sandwiched in between different kind of organic films. And because the whole thing is organic, there is not a lot of density contrast between the membrane filter and the sandwiching films. And the whole thing is only 80 micron thick, so it's not going to absorb a lot of X-rays. And if you look at this sample using tungsten target with the bremsstrahlung or this broad spectrum, even if you lower the applied voltage to 35 keV, in the projection you really don't see anything because all X-rays are just shooting through the sample. But if you use chromium characteristic radiation at 5.4 keV, you can clearly see the pattern that's coming from the membrane filter. And this is just 2D projection, but you can do full CT scan and see an image like this. And because you are creating enough contrast between the sandwiching organic films and the 3 micron thick membrane filter, you can segment them, and you can see some fillers as well. And this can be done by using low energy X-rays, in this case 5.4 keV. So this is about the contrast. We don't want to have low contrast image like this one. You want this. But what about the resolution? We don't want that either. We want high contrast and high resolution image. Those are the two major aspects of image quality. So let's talk about how you can achieve high resolution next. So typical X-ray CT scanners look like this. You have X-ray source here, and you have a sample, and you will be rotating this sample for the scan, and you have a 2D detector at the end. And the resolution of the image you're going to get from this system depends on the focus size and the detector pixel size. And for those two, in general, the smaller, the better. But it also depends on the geometry we use. So this is a simple cone beam geometry, but there is another geometry you can use for high resolution measurements. So this is the cone beam geometry. The name comes from the cone-shaped X-ray beam. And with the cone beam geometry, we use this X-ray divergence to magnify the sample image. And we're gonna talk about this a little bit more in the afternoon in the introduction session. But that's the probably most commonly used geometry for X-ray CT. Then there is a parallel beam geometry that is a little bit different from the cone beam geometry. And again, I'll explain more details about the parallel beam geometry after lunch in the introduction talk. But that one does not use beam divergence for magnification. It uses a regular optical lens for image magnification. Now, cone beam geometry is a versatile and a very convenient geometry to use. But as Tom was mentioning this morning, because of the source size and drift, the source could drift if you do, especially like 5 hours, 10 hours of scan, and you're trying to keep this 5 micron size focus in one place. That's not a trivial thing to do. It would move sometimes, and the size is limited. And this, the size of the focus and also the drift of the X-ray focus, because we're using this X-ray beam divergence for magnification, whatever you have at the source gets magnified as well. Meaning that if the source drifts, that drift is magnified by the beam divergence, and that means you're going to end up having a blur image. And this is one of many reasons why the resolution you can achieve with the cone beam geometry is somewhat limited. But with the parallel beam geometry, because we're not using beam divergence, the source is going to drift anyway, but that drift is not magnified. And the sample is sitting pretty much right up against the detecting system, so you don't need to worry about imaging being blurred. And this is why the parallel beam geometry is considered to be more or less immune to the source drift and the source size limitation too. And it is a really good geometry to use for high resolution measurement. Now, when we talk about resolution, I scan a lot of samples for our customers, and I ask them what kind of resolution would you like to use. And a lot of people say, oh, the higher the better, of course. But the resolution, I think this is the case in any experiment, but is usually in a trade-off relationship with something else. So when you increase the resolution, you're losing something. So instead of trying to get the highest possible resolution, what you want to do is to use the right resolution for your sample. So how high is high enough? How high of a resolution is high enough for your sample? So I'm going to just talk about the sampling resolution. We're going to forget about the focus size and all other things we have to worry about for a second. Let's say that this is the true image of your sample you're trying to measure using X-rays. And to measure something, whatever image you want to measure you have some sort of pixel size to sample this image because you're doing everything digitally. And that pixel size, by the way, is also called the voxel size in X-ray CT because it's a volume. It's 3-dimensional pixels, so it's a voxel size. Now, if you use too large of a voxel size to sample this image, you're going to end up having something like this. So we can tell this is not enough sampling. If you use small enough of sampling size, you're going to see this. This is pretty close to the true image. And the way to tell what would be enough is to think about the smallest feature you're trying to measure. In this case, let's say that whatever fiber or wall is 2 micron thick. If the smallest feature you're trying to image is 2 microns, your sampling size needs to be at least half of it. You can easily tell if it's more than 2 microns, you're not going to be able to see that line. But ideally, you want to have it about quarter, maybe even smaller, but at least it needs to be half of the feature size you're trying to see. Now, I would like to show you what happens if your sampling size or just general resolution is not enough. So this is a CT cross-section of a very low density foam material. And if you scan this sample with about 2 micron resolution, which is relatively high for X-ray CT, but obviously it's not high enough for this sample because we're supposed to see some cell walls in this foam. You can see a little bit of it, but not much of it. If you use 1 micron resolution, it gets a lot better. If you use quarter micron, now you can see all the cell walls very well. And if you zoom into this high resolution scan, you see one of the walls very clearly. And if you look at a cross section of this, you can see that the wall thickness is about 1.6 microns. And this means that your voxel size needs to be probably 0.7, 0.5 microns at least to see this well. So to summarize, if you want to do high resolution and high contrast imaging on low-Z materials or samples, you want to use low energy X-rays. And probably you want to use something other than tungsten to do this. And the parallel beam geometry would be the ideal setup to use for high resolution. And this part I haven't mentioned yet, but you are going to need a pretty high power X-ray source to use low energy and the parallel beam at the same time. And again, in the introduction talk after lunch, I will get more into it. But when you increase the resolution, your scan tends to take longer. The time is another thing you're compromising when you use high resolution. And you could get to the point that the scan could take 30, 40 hours. If you want to do it in a little bit more practical amount of time, you're going to need a high power X-ray source to do this. That's one of the reasons why you need it. Now, one of the systems that I have low energy, high power parallel beam setup is the Nano 3DX. And this is a Rigaku system. And of course, I'm using the Nano 3DX as an example because I work for Rigaku. But most of the CT systems you see in the market are usually using the cone beam geometry for a very good reason. It's very versatile and it's relatively inexpensive to cover a wide range of resolution and field of view. But the Nano 3DX uses a different X-ray source and different geometry to specialize in low-Z material high resolution imaging. So this system has high resolution parallel beam setup, and it uses high contrast, low energy targets such as chromium, copper, molybdenum, additional to tungsten. And it uses a high power source to be specific. The Nano 3DX uses 1200 watts power X-ray source. And I think average X-ray sources and the people use for cone beam geometry is probably about 5 to 100 watts. That's the general range. So you can see 1200 is really high for X-ray CT imaging. And again, high resolution imaging takes long time in general. You can speed it up by using high power X-ray source, and also you can speed it up by using faster detectors like CMOS detector. So you can use that on the Nano 3DX as well. So I would like to show you some examples of CT scans we collected on the Nano 3DX. This is an image of a single, about a 0.5 millimeter diameter particle of, I think that this is a heartburn medication. I just took one particle out of a capsule and scanned it with copper radiation on Nano 3DX. So considering the size of the sample, you can see that this is a very high resolution scan. It's a submicron scan. And the whole thing is organic. It's tiny. There is not a lot of absorption, by the X-rays, by the sample. But you can see different coatings, different layers, different fillers they have in the surface layer. And you can analyze the coating thickness or void, the volume fraction, all those things using software like Dragonfly. This one is ink on paper. Paper is another low Z, low density sample. And with low energy, high resolution scan, you can see the individual fibers in the paper, and also you can see where the ink is going in, how deep the ink goes into the fiber, and where it goes on into. This one is a cranberry seed. The seed is probably about 2-3 millimeters in size. And the whole thing is, again, organic, doesn't absorb a lot of X-rays, but this was a scan with the copper radiation, and you can get a really high contrast image of organic materials like the seed or grains. What else? We've seen cereal as well, so you can see all those things with X-rays. The last one I want to show you is a leg of an ant. This was a scan with chromium radiation. So as you can probably kind of imagine, ants' legs are very, very thin, and it's all organic. So you need to use low energy X-rays to see something like this. And with this resolution, you can see individual hairs on the leg, and that you can do with SEM as well. But with X-rays, you can go inside of the leg and see all the details inside of the leg or any organs of an insect, for example, without destroying the sample. And that's probably the biggest advantage X-ray CT technique has. It's a 3-dimensional imaging technique, and it's non-destructive. Okay, I think that's the last slide. Okay, thank you. If you have any questions, I'm happy to take it.
Questions?
Yes.
You ever run into an occurrence like where you're using your high intensity beam on a low Z material, and the beam interaction actually interacts with the material in a way that causes problems for your imaging?
Yeah, so in general, when you have a mixture of low density and high density samples together, that makes everything really difficult because you can't choose X-ray energy that makes everybody happy, right? The common problem is that you see beam hardening artifacts or metal artifacts from the high density areas. There is a way to get rid of it to some extent with the reconstruction program, but never perfect. So that can be challenging.
How about sample damage itself?
I haven't seen anything visible or noticeable. You might have to worry about it if you use synchrotron beamline, but with the lab source, probably not. No, I don't think I've ever seen it before. I've seen X-rays making call centers, but it's not really changing the structure or damaging it permanently.
Could you repeat the question?
Yeah, I asked about the actual beam damage on very, very soft
the sample.
materials and the high intensity X-rays that they're using, and whether she's encountered any problems.
I can tell you that if you're scanning something live animal or insects, you can kill them. So that's damage.
So you killed the ant.
Yeah, I think we pulled the leg out of the cell to scan it. That's actually a millipede. That image.
Bringing up flies lately?
I had a had a friend of mine at one point that was describing a new technique they were using to doing like in vivo work. And he explained to me how it happened. We were designing a source for him. I said, well, what happens to the mice? And he goes, well, this doesn't end well for our fur. So there's certainly some damage that can be done. Yeah? All set? Okay, thanks, Kanaya.
Thank you.
So our next speaker, and the final one for the morning, is Professor Kostya Kornev from Clemson. And before I read the biography, I'm going to tell you one thing, is that Kostya is actually a theoretical physicist posing in clever disguise as a molecular biologist. So everyone keep on your toes. Yeah. So Kostya leads the micro and the nanophyletic system research group in the Department of Materials Science and Engineering at Clemson. No booze from the LSU people, please. Okay. He graduated with a PhD in physics and mathematics from Kazan State University in the Soviet Union in 1988. In 1990, he was invited to join the Institute for Problems in Mechanics of the Russian Academy of Science in Moscow. In 2000, he joined the Textile Research Institute in Princeton and moved to Clemson in 2006. His research interests include arthropod-inspired materials, insect biomechanics, wetting and capillary phenomena in magnetic materials. In 2016, he was elected the president of the Fiber Society, and in 2018, he received the Founders Award of the Fiber Society. So, Kostya.
Thank you very much, Tom, for the introduction. And I understand the purpose of this talk is to give you some different angle of looking at the things not directly related, and I will try to through a bridge between what I'm going to talk about and what we heard recently. And so far this workshop was quite exciting and I learned a lot, but today I'm going to talk and jump from the exciting fiber that insects are using for different purposes, and bring that fiber in connection with microfluidics. Okay, so these basic two examples I am going to cover. And the first thing is related to hydrophobic hydrophilic dichotomy that insects are using every day. And we don't know about that, and we didn't even think about that before we started that research. And then I will show how to use that kind of thing in artificial fibers and artificial materials. So the first slide is an introduction to the topics I'm going to discuss, but this is the biggest formula you will see. So what we know about the surfaces and interactions of liquids and solid with the surfaces, that you can say some surfaces are wettable, some are not wettable, but quantitative characteristic from the material standpoint is the surface energy or surface tensions. If you are a mechanical engineer, you would prefer to call it surface tension. If you are a material scientist, you would prefer to call it surface energy. But basically, if you place a drop on the flat substrate, you will see that drop either try to wet that substrate, making a very thin puddle, so the contact angle is less than 90 degrees. The contact angle you are counting from the substrate internal contact angle and the tangent vector at the surface of the drop. If the material is not wet or poorly wettable, that drop is going to be beating on the substrate. So, and industry tries to kind of defeat that paradox using very simple material and making material to work as hydrophilic, even if the material, the chemistry is supposed to be hydrophobic, or vice versa, right? So, and I will show you the trick how to do that. And the big difference between that ideal situation and the real situation, we saw excellent tomography images of the fibrous material. So if you have a drop and that drop is placed on the fiber, you will be amazed that even the material is completely hydrophilic, zero contact angle, with a flat surface. So on that fiber, the drop is going to be beating, making impossible to wet the fiber completely, right? And that is very interesting trick that nature are using all the time. Butterflies or this poor ant cannot get out of the droplets on the leaf. So, and I'm going to talk about a little bit what the shape is bringing to the story, and how this chemistry and the shape are going to work together. So this is the Darwin moth, and you see it has a very long, very interesting fiber, because that fiber brings sensors. It has different actuators, because when butterfly is not hungry, so that very long fiber is going to be packed in the tight coil. Right, so that is a packaging problem. It is solved by nature. That is why you want to see more carefully what is happening with that fiber. And remember, that is a feeding device, right? So the insect has to deliver the fluid to the digestion channel. So, and that fiber appears to be made of two strands coming together and forming the food canal, we see here. Right, and these strands, I don't touch how they mechanically engage to make that strong fiber, but you see in a second that the structure, that is a cross section, the structure is quite complex. It has two tracheas, again fibers, which deliver the air. So, and these are the holes for the blood. So it's again little things. So. There are different questions biologists ask, there are different questions physicists ask, and there are different questions engineers ask. And you can learn a lot talking to different people. So, and I will go into to show that one amazing thing we learned, that actually that fiber has very different weighting properties. You see the drop at the top is beating up, but if at the end of the fiber, when you dip into the liquid, the meniscus is climbing up. So, and in a second that I help us to take these images, and you see that proboscis is very complex in nature. So, and interestingly enough, that if you ask yourself whether butterfly use the drinking straw mode to pick up the fluid, it appears quite challenging, because at the tip of the proboscis there is no hole to pick up the liquid. Okay, so this is the food canal, the head somewhere here. So, and this is the tip of the proboscis, that these two fibers are forming the food canal, and at the end, at the apical ends, there is no hole. How come this happens? So, and the interesting story that if you look at the microscope, that is not X-ray, this real microscope. So inverted microscope, if you look at these fibers, so basically butterfly presses the proboscis, bending the fiber down to the source of liquid. This is paper towel soaked in the sweet solution of sugar, and in nature habitat, this method is called paddling. So it has nothing to do with the puddle of water. Typically, butterfly they are looking for calcium to get some mineral water out. So now, if not the drinking straw, but still in order to estimate the needed pressure, so how this happens, so you will see again that this is the head of the butterfly, and this is the pump the butterfly uses, so pressing the nerves up and down, so it pushing the liquid out and picking it up. And if you calculate the pressure, you will be amazed that the pressure required to draw that liquid is about 1 atmosphere. So no one vacuum pump on Earth can produce such a great pressure, right? And that is for the monarch, but Darwin moss has much greater pressure equivalent to the column of air of about 1 meter square. The weight you have to lift up in order to suck the fluid. So how this happens now? We went to Oregon National Lab, and I learned recently from Tom that Daria Monaenko, she was my graduate student. Now she's working at Dow, working with Tom. So, and she went to Oregon Lab, and that is a setup. So on the APS synchrotron. So what you'll see that is a needle pressing the proboscis down. All the dark part is a cuticle. It's made of chitin. It's like looking like your nails, which is made of different material, keratin. But the foot canal, when it's empty, you are going to see it's bright, right? And what is happening now? You'll see that that is the proboscis of live butterfly. So butterfly is not that. It is happy, and the power source is very low. It's about 3.2 kilo electron volts. So, and this is a tube, and you'll see what happens with that. So, actually, do you see the bubbles? So, what butterfly does, touching the wall of the tube with a liquid on it. So it creates the bubble trains, right? So actually it doesn't suck up the continuum liquid column, but it drinks bubbles, right? It drinks little liquid bridges between bubbles. So that is a source of liquid. So now you can answer the question why this happens. There is another experiment very much similar. So place a drop on the side of the proboscis to see actually whether the proboscis is permeable or not. Is it how this happens? This is a big drop. This is the end of the needle. We release the drop from the needle, and now you see the foot canal is here. The brighter, the dark is the cuticle. The other fiber, right? Now you'll see what happens. This is more clear now that we released the needle. So watch what happens. You see these liquid bridges forming up immediately. So, and actually the head is up here. So butterfly sucks up these little liquid bridges, and the bubbles significantly reduce the friction. So this is a smart way of drinking, because now if you look at what the diet of the butterfly, some of them they are able to drink honey. So, and with that long proboscis, which is about 100 micron, like your hair, so they are able to drink honey just because of that effect. Right, they are not drinking liquid columns, right, which is impossible to move, right? But they are drinking little bridges, liquid bridges, and that's enough for them to. Yes.
So as that feeding tube oscillates back and forth like this, does that compression change the porosity of the cuticle?
I wouldn't claim that. We didn't measure that. That is right now on the question. Most likely, yes. Right, but what you see, the vibration, it comes from the pump of the butterfly, right? So it creates the pressure differential all the time. Each stroke gives you pressure differential. Most likely.
And how are you capturing that image?
See, it's again the picture is that. It's very much similar. So we just laid the butterfly on the top of the substrate, and that's it. Okay, so you cannot see there, right? So you have to put it on a manipulator. Okay, so now the engineering equation immediately comes up, how quickly that meniscus forms, right? And where you can talk about the macroscopic meniscus, and when you can separate some size effects, right? And the proboscises of butterflies varies significantly. So the very small proboscises are measured in microns, right? The largest proboscis, the diameters of the foot canal measured in hundreds of microns, right? So that is the simplest setup you can imagine. So that is a tube, right? And you gently, with a manipulator, gently touch it with water or some other fluid, right? And again, going to argon, you can watch how this happens, how the meniscus nucleates and how it forms. And amazingly, all the textbooks are saying, okay, the meniscus would first nucleate and then it stays there. So the initial condition for mechanical engineering velocity is 0. This never happens. So once that the meniscus nucleates, it rushes in immediately. It wants to wet the material, so and the velocity is pretty fast. So we were able to catch only 4 to 5 images, about 32 frames per second. So it's amazing how this happens. So it's completely dynamic feature, not thermodynamic feature for material scientists. It's just out of question. So, and we are trying to understand how this happens. Okay, so with that said, it seems we brought some good things with X-ray analysis, and now what happens? Another application, what happens with wetting on demand, and these are materials typically are considered for microfluidics, and these are example of microfluidic devices. Even if you don't know about that, if you go to the medical exams, for example, your blood is going to be analyzed that way. Right now, it's very simple. So a little drop of the blood is sitting here, and it moves through different channel, and different sensor are studying the composition of that blood. Okay, but paradoxically, so the material that chips are made of is limited in composition. So majority of materials, and we heard about it, so are actually all the polymers are listed here. This is a basic market in US, right? And surprisingly, all these polymers, they don't like to be wet by water. So they are poorly wettable by aqueous solutions. Now, definitely you want your microfluidics to be inexpensive, right? So you want to use those polymers available, and how to make them inexpensive. The first thing to think about making them very simply way, right? And just to spin the fiber. Using those polymer and make the fiber shaped with multiple channels on it, and chop them in sequence, and that will be your device, right? But the problem of wettability is still present. So, and again, we look at the insect, and you will be surprised to see that majority of channels, for example, in the proboscis of fly or in proboscis of butterfly, they are C-shaped. If you look closely, so you will see that these surrounding things are C-shaped. So the nature doesn't like the sharp edges. But again, if you go back, so all these trenches are sharp edges, right? So what we want to do is to learn whether this C-shaped fiber will bring something to the table which is not allowed with the sharp edges, right? And first thing, we look at the shape of the liquid inside of the liquid drop inside the proboscis. So we spread the proboscis in 2 pieces because it's natural. And look how this meniscus behaves. And somewhere here you will see it's completely connected, intact, and then somewhere here it takes on the crescent shape, right? So, and it wet the interior, right? So exterior, as I said, hydrophobic, but interior is hydrophilic. Now, with that idea in mind, we went down to develop the straightforward but not simple as seemed in the first place methodology how to make different channels just with a molding technique. But important thing and the most important task was to vary the angle of opening, right? We want to study that and how to pick up the right design. And you see that if you play the drop on the material which is not completely hydrophobic, so you will see the contact angle is 93 degree. A liquid gets inside, but if the contact angle is greater, you can keep the channel clean, right? That's important thing. Now the question is, can you actually flush the liquid through the channel, so making the interior wettable? Right. Again, so looking at the cross section of a different position of the droplets, you can learn a lot about the wetting properties of the material, and that is an example. That is a droplet beating up on the substrate, and you see we call it clamshell-like drop, right? So in the material science terminology, you would say that is a representative of non-wettable material, right? So because it's easy to shake it off, right? Now, if you go on, but importantly, also observe that these ages, the places where the drop is pinned, right? So now, if you change a little bit the design, not changing the wettability, material is the same, you will see that drop actually spreads over the channel, right, making the meniscus with a dimple. So this is a column, so we call material wettable. Now, what Mike showed that was very fascinating thing. So students unfortunately didn't know about your software. So and everything what has been done is using ImageJ and MATLAB coding. But what we were looking at is the curvature of that meniscus, right, at different positions. Right, and using all this stack of images, we analyze curvature to see that actually this is a column. The curvature remains constant all the way from one edge to the other, right? Only at the ends when the liquid wants to meet the substrate, it changes, right? So meaning that is a wettable situation completely. Now, if you start changing different fluids, right? So what you'll see that actually you may have the clamshell-like drop, right? Or when the curvature changes, so that is a cross section, and also you'll start seeing the columns which are changing in length at the same time they do wet the material, right? And that is analysis. It's quite tedious, but you can do that. And at the end of the day, so material scientists would love to have some phase diagram, and this is a phase diagram. So this is a contact angle, the physical properties of the material, right? And the liquid, so the wear, and this is a half of the opening angle, so the design of the channel. And as you see, even mercury can wet that channel. So you see the contact angle is greater than 90 degrees, but the channel is wettable, right? So with that said, as you see that the tomography here, X-ray tomography, is a very important tool for different applications. I'm not talking about the resolution here, it is really an issue. As I said, I didn't know in advance about that big progress in analysis of images, but the message is that, so unfortunately we cannot completely clone the design that the insects are using, but we can be inspired by that design and we can make something out of it. And the good friend of mine, Peter Adler, he introduced his entomology. He introduced me to the insect world, and Eddie Bird is his research associate. Wahid Lee, he was working at the Argonne National Lab. Now he moved to Brookhaven Lab. So, and directs one of the beamline there, and we are working in direct contact. And Daria, she was one of the first students who worked on that project of butterfly, but now it's about 5 generations of students continue picking up different challenges. Thank you very much for the invitation, and I'll be happy to answer
Questions?
Go ahead.
A couple of slides ago, you actually mentioned the vertibility as a function of the opening angle. You make the angle, this one. Yeah, this one.
Yes.
Is it a function of the diameter also?
You normalize everything by the diameter. The only characteristic length scale is the diameter of your channel.
Huh?
Yes. Okay.
Anyone else? Okay, let's
Thank you.